We're talking about electric fields. We even calculated the electric field from a point charge. Electric fields, and the lines that we use to represent them on our papers, can be quite useful. There are a number of rules that we have to follow when we're drawing electric field lines. And if we follow those rules, then we know something about the charges and the electric fields when we look at an electric field diagram. The first thing we know is that electric fields originate on positive charges and terminate on negative charges. We had to pick something. That's what we picked. It's just the definition. Another way to remember that is that the electric field points the direction a positive charge would go if we put it at that location and let go of it. Another thing to remember is that the electric field direction, in addition to pointing in the direction a positive charge would go if you put it there, the electric field direction is tangent to the electric field line. That's the way we draw them. The lines are continuous curves, but if you were standing at some point in space with your electric field meter, it would point tangent to that line. The magnitude of the electric field is proportional to the density of the electric field lines. So where the lines are closer together, it means the electric field is stronger. And the number of electric field lines originating or terminating on a charged object is proportional to the charge of that object. All right, let's go through these real quickly, looking at a point charge. If we have a point charge here, let's make it a positive one. We know that the electric field will come out of that positive charge. The positive charge will fill the space around it with an electric field, and those field lines will point radially outward. Electric field lines originate on positive charges, like I've drawn here, and they terminate on negative charges. If I had a negative charge, those electric field lines would point the other direction. Now let's put a positive charge and a negative charge together. If we had a positive charge and a negative charge sitting in the same region of space, the electric field line would come out of the positive charge. Instead of coming out, as we're seeing in this picture, straight in all directions, it would be influenced by the negative charge. As that field line comes out, it wants to find that negative charge to terminate on. So one of the electric field lines will look like this, and the one that comes out like this will actually come around and terminate into that negative charge. And there's probably another one that comes out and loops around like that, and maybe one that comes out and loops in this way. My paper is not big enough to draw that. One that comes out here and goes out to infinity, and one that comes in from infinity and terminates there. Something like that. So our drawing would look something like this. Remember that these two actually connect out here. If our drawing goes all the way out to infinity, we would see those two connect. And the same with these two. Those would connect at some point. So the field lines originate on positive charges and terminate on negative charges. Now, if we wanted to know, what else do we, the direction of the electric field at some point. We want to know at this point, what's the direction of the electric field? Well, the electric field is tangent to the electric field line. So the electric field would point in this direction at that point. And if we wanted to know the electric field, the direction of the electric field over here, well, it's tangent to the electric field line. so it would point in that direction. And if we wanted to know the direction of the electric field over here, it's tangent to the electric field line there. You get the idea. Now the magnitude of the electric field is proportional to the density of the field line. So let's look first at this picture. The field line's just a positive charge sitting all by itself in space, nothing else around it. And the field line's radially outward, coming radially outward from that charge. So where are the lines closest together? In here, close to the charge, the lines are close together. Out here, they're very far apart. That means that as we get closer to this charge, because the density of the field lines is increasing, the electric field is also increasing. The density of the field lines is proportional to the magnitude of the electric field if we drew our field lines correctly. So this tells us the same thing. In here, the electric field is strong. Out here, it's weak. And we can see that just by the density of the electric field lines. And the last thing, the number of electric field lines originating or terminating on a charge is proportional to the charge. So here I have a negative and a positive, two charges. And let's count the field lines. I've got 1, 2, 3, 4, 5, 6, 7, 8. I have 8 lines originating on that positive charge. So the charge has to be proportional to 8. Who knows what it is? Maybe it's 1 microcoulomb, maybe it's 100 microcoulombs, maybe it's something else. But that charge is going to be proportional to 8 lines coming out of it. Now, any other charge that we see that has 8 lines is going to be the same magnitude of charge. So let's take a look at our negative. Our negative has 1, 2, 3, 4, 5, 6, 7, 8 lines going into it. So those two, because they have the same number of electric field lines associated with them, their charge has to be the same, whatever it is. Maybe it's 5 microcoulombs, maybe it's 5 coulombs, maybe it's 100 coulombs, I don't know, but they have to be the same. If one of those charges had 4 lines and the other one had 8, the one with 8 would have to have twice as much charge as the one with 4. They're proportional. Let's quickly review what we get when we look for the electric field from a single point charge. If we have a point charge here, I'll just use capital Q for my charge. And we want to know what is the electric field at this point right here. We can use this equation. Just like finding the electric force between two charges, I would use this to find the magnitude of the electric field. And then I would look in and assign a direction, because it's so easy to look at this and know what the direction is. I would do it that way. But if you do that, you don't forget you're taking the magnitude of the charge. So let's take a look at each one of these things real quickly. If I'm finding the magnitude of the electric field, I would take the magnitude of the charge and I would divide it by the distance between them. The distance, remember, think about each variable in your equation. What is this little r? It's the distance from our point charge to our point of interest, the place where we want to know what the electric field is. so that would be this distance right here. And of course, we need direction for an electric field. So I would look at this scenario, and I'd say this is a positive charge. So the electric field is going to point away from it. So at the location of my point of interest, the place I want to know what the electric field is, the electric field would point away from that positive charge. If I drew that line back, from the positive charge, it would go radially outward. That was the electric field from a single point charge. Let's take a look at finding the electric field from multiple point charges. I'll use 3. Let's make Q1 and Q2 positive, and Q3 negative. And we're trying to find the electric field at some point in space. How about at this point right here? We can use the principle of superposition. Find the electric field from each of the point charges individually and do the vector addition and add them up. Let's look at Q1's electric field first. I'll use green for Q1. And if I draw a straight line from Q1 to that point, the electric field would continue in that direction. I'll call that E1. The electric field due to Q1 would point like that. If no other charges were in this region of space, that would be our electric field just due to Q1. Now we do the same thing for Q2. I'll use blue for Q2, and I draw a line straight from Q2, and that would be E2, would point roughly in that direction, radially outward from the positive charge. Now I do the same thing for 3. I'll use gray. Draw a straight line. Now this is a negative charge, so its electric field points toward the negative charge. So there are my 3 charges. What do? I do my principle of superposition. I've got E1 points something like this. E2 points like that, so I add my vectors tip to tail. E3 points something like this. So my final vector would point in that general direction. E net is equal to the electric field from charge 1 plus the electric field from charge 2 plus the electric field from charge 3, vector addition. So at our location, the electric field, I just have to translate this up to my location of interest, would point somewhere in this direction, the way I drew it here. Of course, it depends on the magnitudes of those charges, but the way I drew it, it would look something like that. Let's take a look at an application of electrostatics you might not have thought of, a photocopy machine. The key to the photocopy machine is something called a photoconductor, a material whose conductivity changes when it's exposed to light. Figure 1 shows that electric charge is placed over a drum. Figure 2 shows light hitting that drum. Where does that light come from? Well, it's reflected off of a piece of paper. The piece of paper probably has black text written on a white piece of paper. The black text absorbs the light and does not reflect it, but the white areas reflect the light onto our drum, and that makes it conducting in those areas, and we lose the charge from all the areas that are white on our piece of paper, cause the charge to disappear, to dissipate off of that photoconductor. The only places on our drum where there's charge are the places where we have text on our piece of paper. Then you sprinkle charged toner, that's the ink, onto the page. It sticks to where there's electric charge. That gets transferred onto a piece of paper and then heated, and that toner becomes permanent on the piece of paper. Relatively simple, except for this photoconductor, this material that changes conductivity with exposure to light. Very cool application of electrostatics.